Okay, let's begin. Welcome to the last seminar of the year, brought to you by the PYSQT network. I will present a speaker in a minute, but first, let me remind you that we are open for contributions. I think my colleagues are going to leave the link to our Google form in the chat at some point. Yeah. So I invite you to click on it and propose yourself to give a future seminar. And you can also suggest senior speakers that can perhaps give a more review style keynote or seminar on a more general topic. With that, let's move to today's seminar. Our speaker is Nadir Samos. He studied physics at Universidad de Valladolid. He did a master in theoretical physics at Universidad Complutense de Madrid. And then he did his PhD on entanglement in inhomogeneous quantum chains at Instituto de Física Teórica and Universidad Autónoma de Madrid, under the supervision of Germán Sierra and Javier Rodríguez Laguna. For the last year, he has been working as a postdoc here at INMA with us. And today he's going to explain some of the work that he's carried out this past year. Nadir, you can take it from here. The floor is yours.
Okay, well, hi everyone, and thank you, Juan, for inviting me, and well, Juan and the organizers for inviting me to give this last seminar of the year. So today I will be talking about two topics that I believe that are hot topics in theoretical physics. The first one is barren plateaus, which they appear in the framework of quantum machine learning and variational quantum algorithms. And the second one is a bit older, I think, is quantum complexity, and it's from high energy physics, black hole physics, but now it's of paramount importance in many fields. So, well, I will try to make this talk self-contained, more or less. I'm not an expert. This is a bit of disclaimer, but of course, feel free of interrupting me whenever you want. And let's go. So I will start first talking about barren plateaus, which arises in the context of quantum machine learning. So let us give some definitions first. So we start with classical machine learning, and a classical definition of classical machine learning, which is this one of Arthur Samuel, which is the field of study that gives the computer the ability to learn without being explicitly programmed. With this definition, it is obvious that we can make a naive definition of quantum machine learning, that would be just by substituting computer, but by quantum computer. So, of course, this quantum machine learning then will leverage all the power of quantum computers, and this is the large dimension of the Hilbert space, and enjoy the quantumness on the power of the qubit, alias the quantum entanglement, superposition, and reach the so-called quantum supremacy, which is defined as the situation when a quantum computer can perform a task much faster than a classical computer. So this is the hope, and this is our horizon. But now we are in a different reality, which is a nice reality, but so because we have quantum computers, but they have a limited number of qubits, and also the connectivity is limited. And moreover, the quantumness, this is the things that make them quantum, last a few times, like the coherence times. So this is we are living in the noise intermediate scale quantum computers era. And one question is if we can reach the quantum supremacy with this kind of computers, or we have to wait until we get the other ones. But with respect to quantum machine learning, we can make a new definition, which is the field of study that gives the niche computers and classical computers the ability to learn without being explicitly programmed. And you see that I have put here classical computers also, and this is the case of the variational quantum algorithms. Because, well, first, let me say that in quantum machine learning, we deal with data, and we expect that this data is from the real world. So we need to make a previous task, which is hard and is absolutely non-trivial, which is the map the classical data to Hilbert space, to quantum states. And this indeed poses an additional problem that I will not discuss here. So I will be talking about the variational quantum algorithms, or VQA, which are the leading strategy to achieve the quantum supremacy. And in this context, so we don't have the need of making this map of classical data. We assume that we start from the beginning with something quantum. There are many kinds of variational quantum algorithms. I will explain what is it with a particular example, which is the variational quantum eigensolver. Which the objective of this VQA is to find the ground state of a given Hamiltonian. So the first thing to do is to define a cost function or loss function, which is in this case the energy. And our duty, or the thing that this VQA must do, is to find the ground state. This is the state that minimizes the energy. So, of course, this Hamiltonian is expected to be something which is difficult to compute in the classical computer. But because it is, as it is quantum, we expect to do it better in the quantum computer. So the second step is to design a circuit, which is of course a big unitary that depends on a lot of parameters, which I label theta, and this you must see it as a huge vector of many parameters. So indeed, we can also write this unitary in terms of product of other unitaries, which are the layers of the circuit. So I have made this beautiful drawing to show this. Here you have this the quantum part and classical part. And you see that in the quantum, we have the circuit, we have a fiducial state, we start with it, and we perform this computation in the quantum computer, and then the output is passed to a classical computer. And this classical computer performs the optimization and try to find what is the optimal values of these parameters to find the minimum. So you see that this is, of course, we iterate this, and you see that this is a mixed operation when that involves the quantum and the classical computer. So, of course, the cost function must enjoy some properties, reasonable properties. It must have a minimum or an optima to find, and also our circuit must be able to reach the solution. This means that there exists a configuration of these parameters that yields the solution or a good approximation. So let me be a bit more clear about this. Suppose that we have a circuit 1, and we denote by capital U the subset of solutions, or the subset of unitaries that we can achieve by varying the parameters of the circuit 1. And we can do the same with a circuit 2, and let's name the same capital U2. So you see that in this case, the capital U2 is the area, which is the red part, is bigger than the U1. And the gray part is the whole unitary group. So clearly, it is more likely to have a solution for the circuit 2 because it's bigger. So if you have a problem and you have the circuit 2, it's likely the solution is likely to be there. And we say that in the language of the PQAs that U2 is more expressible than U1. And this is the concept of expressibility that I will develop a bit more. But with this picture, we have a naive question, which is, okay, so the better circuit will be the one that allows to explore the whole unitary group. So can we design it? It is possible to have this circuit? And the answer is no. No, because efficiency, of course, it's possible, but it takes exponential time. Why? Because the circuits that we consider are made of 2-qubit gates, are made of unitary gates, and that's why the color is different. But the important thing is that they are 2-qubit gates. And there is another result from Neil that say that in order to sample uniformly from the unitary group, we need 4 to the n and bane n the number of qubits gates. So this explodes dramatically. And so as a matter of fact, we cannot do this sampling. But what is this? What I mean by sample uniformly? So the answer is the Haar measure, which is the analog, I would say, of the measure of a sphere. So let us think first in the sphere case. So when you want to compute the volume of this, you need to take into account the determinant of the Jacobian, which is the infinitesimal volume, and tells you that the volume at the equator is different than at the poles. So if you want to sample points from the sphere, you have to take into account that, because there should be more points at the equator than at the poles, because the volume is bigger. So this is the measure. And if we talk about the unitary group, the Haar measure do exactly the same. It allows us to weight properly the elements and to sample uniformly from the whole unitary group. So the Haar measure enjoys nice properties. Of course, it is normalized to 1. But the nice property is the left-right invariance. So you see that here we are performing an integration over the whole unitary group. This is also called an average over the unitary group. But the fact is that we are considering an arbitrary function, and inside the function we have the product u v being unitary. And this is equal to, UV, and this is equal to BU, and this is equal to U. And this for every unitary V. So this is the left-right invariance that only happens if we are integrating with the Haar measure. And this is a very nice property. And to see that, well, first, a bit of terminology. This is the k-fold channel or k-fold twirl also on Haar is defined as this superoperator. Then you see that this is an integration over the Haar measure with the whole unitary group, and we are taking a tensor product of unitaries and an operator X and the daggers also. So this is, as I say, this is the k-fold channel, and the nice property of the Haar measure is that because of it, we see that this k-fold channel commutes with the tensor product of unitaries. So we can use a very well-known theorem in group theory, which is the Whale-Shur duality. And this allows us to write the average of the operator X in the unitary group or this k-fold twirl as function of operations on the symmetric on the permutation group or symmetric group. And just to remind you, if k equals 1, we have only one operator, which is the identity, and if k equals 2, we have the identity and the swap. So this is just a curiosity. This is the Weingarten calculus, and because of this, we like to work with her, because we know how to compute these things. We know how to compute these averages. Okay, so we close the parentheses. That's what we mean by sample uniformly. The next question is, do we really need it? Do we really need to explore this whole unitary group? The answer is yes, but maybe with some restrictions. And let me be more specific. And here I introduce to you the concept of unitary K designs, which are of paramount importance in many fields also. And the idea is that we can consider a subset or a finite set of unitaries with a probability associated to it, of course normalized to 1, and these unitaries enjoy a grid property. The idea of a K design is that if we consider a k-fold channel over this ensemble, then over a given operator x, this average is equal to perform the average over the Haar with the Haar measure, as I told you in the previous slide. So I think that with this picture, it's more or less clear. With this in the right-hand side, we are integrating over the whole unitary group, so we are considering the whole plane. But with the ensemble, we are considering a finite number of unitaries, and if it is a K design, we know that this is an equality. So this is super good, because we only need to perform operations with a finite number of unitaries. So there are theorems of existence, but we know few sets or few results of K designs. We know, for instance, that the Pauli group is a 1 design. I remember that the Pauli group is the set of operations that are obtained by tensor product Paulis and the identity, and also the Clifford group, which is the operation that sends the Pauli strings into Pauli strings. It is known to be a 3 design. If it is a 3 design, it is also a 2 design and a 1 design. But and this is general. If you have a K design, you know that it is a K-1, K-2, etc. But of course, you know if the K+1 is also a K+1 design, and this is not correct in general. So why this is important? Because if we want to compute an average, imagine that we want to compute just a normal average, and this average will involve only a copy, one unitary. I mean, one unitary here and one unitary here. Then you, if you have a unitary design, a 1 design, you know that the result will be the same, that averaging over the whole unitary group. So if you want to compute something to the K level, and if you have a K design, you have the most expressible ansatz you can have, but cheaper, or with a very much less exponential cost, I would say. So since we know few things about the exact unitary designs, the better thing we can do is to relax the definition and to talk about approximate unitary K designs. And as you can imagine, this is just the difference of how far we are from having an exact K design. So this epsilon which depends on the operator x, is just the 2 norm over and the difference between the k-fold twirl over the ensemble and the k-fold twirl over the har with the har measure. So, and of course, if this epsilon is 0, we have the k design. Okay. So this is good because by using again the left-right invariance of the Har measure, you can show that this norm is equal to the trace of these two elements. And if we now restrict ourselves to the operator x being a density operator, thanks to the cyclicity of the trace, you see that the approximate K design is defined in terms of the fidelities. You see, these are the product of two states, and this is the fidelity with to the power of K, basically. So this is, of course, in the Har, this integral with Har, we know how to compute it with the Weingarten calculus that I showed you before. And this depends on the ensemble, but maybe with numerics, it's easy to do. Okay, so coming back to our original slide, I have tried to convince you that we don't really need to cover the whole unitary group, but we maybe need a K design, and that depends on what we want to compute. But there is no doubt that this is cheaper in terms of cost. And indeed, it was shown by Brandau et al. That these random quantum circuits are K designs, and the depth of the circuits grows linearly and not exponentially. So this is a very a great advantage. Okay, so well, what about the barren plateaus, right? Because so far I have not talked about it, but now we are in a good position to do it. So nowadays we have there are a lot of literature about the barren plateaus because it's a very hot topic. I have put here these two papers that I believe that they are cornerstones. This left one of McLean et al., I think that it is the foundational paper. And so remember, I will define the barren plateau. Remember that we have a cost function and we want to find the minimum. Okay, so at some point we will compute the derivatives with respect to the parameters and consider, for instance, this theta k over which is the parameter in some layer, in some unitary inside the big circuit. The barren plateau is defined by two ingredients. On the one hand, the average over this derivative of the cost function is 0. And secondly, the variance of this derivative tends to 0. And with these two ingredients, what we have, if this happens, is that the derivative is 0, meaning that there is no slope, there is no way to find the minimum. And moreover, the variance, as also it tends to 0, this using probability or statistical properties like the Chebyshev inequality or concentration of measure lemmas like the Levy's lemma, what happens is that it's impossible, or it takes an exponential cost to find the minima, because there is no way to find what is the good direction to go, where is the minimum. So this poses a problem in the trainability of the ansatz. And the fact is that if we have barren plateaus, the ansatz cannot be trained because it takes an exponential time to find the minimum. Assuming, of course, that there is a minima, but we have assumed that the cost function is well defined. So the mission is to avoid the barren plateaus. That is, and there is, as I have said, a lot of literature. And of course, I must also say that there are many sources of barren plateaus. Here, I will be talking just about one, which is the one related with the randomness, but there are more. Now it's important to distinguish the two kinds of cost functions. We have the local cost functions, which as if we consider a Hamiltonian, this means that the Hamiltonian there is formed by an operator which is its support is trivial in the majority of sites, but non-trivial in just a few sites. That's a local Hamiltonian. And a global cost function is the case when this is not true and you have a non-trivial support in all the sites of the operators. So this distinction is very important because what these two papers show is that making the assumption of that the circuit is a two design. And why is a two design? Because you see that here we are computing the variance, and the variance involves the product of two density matrices. So we are having two copies of the unitaries, and that's why we restrict ourselves to a two design. If we have a two design, we have the maximum possible ansatz, expressible ansatz. So what they say and what they show is that if you have a global cost function, first the barren plateau conditions fulfills. The average is 0 and the variance goes with the inverse of the dimension of the Hilbert space. And you can imagine that this is very bad, because if you are having a proper quantum computer with 1000 qubits, this is 0. So the cost function and the ansatz, the variational quantum algorithm, is not trainable. And indeed, in this other paper, they show that even relaxing the two design assumption, there is, and having a global cost function, the ansatz cannot be trained. So the nature of the cost function is crucial. And in this paper also, in the Sáenz et al., show that if we consider a local cost function, that this is the other case, we have that the average is 0, but the variance is greater or equal than the inverse of the 2 to the power of L, where L is the number of layers. So this opens a window of trainability, because if now we consider L being log n, this is a small number, and also the non-trivial part of the operator must be really non-trivial, must be far from the identity, then they show that it is possible to train. There is a region where there are no barren plateaus in principle. So summarizing this, the nature of the cost function is crucial, and we have to avoid the barren plateaus, the global cost function, because even with inexpressive ansatz, this is with ansatz with no depth, we can find a barren plateau if we have a global cost function. So we have to avoid it. But also, if we consider highly precise ansatz, this is two designs, we cannot train, because there are barren plateaus. So I have been talking about the trainability related with the barren plateaus, and before with the expressibility, which is behind the concept of two design and approximate K designs. So what is the exact relation? Well, there is a paper, a very nice paper by Sui Holmes et al. That give precisely an answer to this. And they find that the variance is upper bounded by a quantity which is like before. This is the case where you have maximum expressibility, or you have the two design, but there is an additional term. This is a function. We don't care too much about it now, but the point is that this is a positive function, and the arguments here are just the definition of the approximate K design that I put you. I put slides before. So you see that if this is non-zero, we have a window of trainability. So the message by Holmes et al. is the following: the more expressive the ansatz is, the less trainable it becomes. So the solution to this, apparently, and a good solution, because it has been proved that it is a good solution, is to make ansatz that are tailored to a given task. So forget about the expressivity. Forget about the nice idea of having like a black box where you can put whatever, and the black box will have the solution for all the problems. You have to modify this black box, this ansatz for each problem by hand, and this work. But well, I would like to know if there is on a other way around, if we can bypass this constraint, which is very rigorous for sure. So we take inspiration for the many-body physics area, and there we know that there is a way of slicing the Hilbert space, which is very good and very interesting, which is doing it in terms of entanglement. So in terms of entanglement, it turns out that the vast majority of the states follow the so-called the area law, the volume law. What is this? The entanglement entropy of a given subsystem is proportional to the volume of the subsystem. So it grows linearly. And indeed, there is a very old result by Page that he proves that the vast majority of these states has almost the maximal entanglement, which is the system size times log2. And there is another corner of states, and I mean corner because it is very small compared to the huge, the size of the Hilbert space, which is the area law corner. And this area law corner englobes all the states whose entanglement entropy is proportional to the boundary. And with this picture, I want to show that the area law state is the one who has short-range entanglement. This is the degrees of freedom that are close to the boundary are the ones that are entangled to the rest, and that's why the entanglement is proportional to the boundary. So it happens that there is a great majority of ground states, for instance, that enjoy this property of the entanglement. So, and indeed in 1D, there is a rigorous theorem due to Hastings that proves that if you have a gap Hamiltonian, this is a Hamiltonian whose spectrum has a gap, then the ground state enjoy this short-range entanglement and obey the area law. So, according to this, or based on this knowledge, there are many classical results and classical methods like the DMRD or tensor networks and matrix product states that are super successful in diagonalizing and finding ground states and with a classical computer. So one question, of course, if there is room of improvement with the quantum computer, but as a proof of concept, that's good. So what I mean, what happens if we restrict our ansatz with entanglement? What happens if we allow our circuit to reach some entanglement, but not the maximum? So to do so, we have the bond dimension and the matrix product states that allows us to slice the Hilbert space in terms of entanglement. So the random matrix product states are matrix product states as usual. So you have that the amplitudes are obtained by multiplying terms which are local, and they describe local degrees of freedom. And these matrices A are obtained by tracing from the physical part and leaving the ancillary one over a unitary which is random, which is dragged from or sampled from the unitary group. So this is the picture. This is the typical matrix product state, and the difference here on the random part comes from because this A comes from this unitary, and you slice it properly, and you have in this case you have two matrices, A0 and A1. And of course, if this unitary is the same for all the sides, you have an homogeneous random matrix product state, and if it is not, it's an inhomogeneous random matrix product state. So the question is, or now, of course, because this is a unitary sampled with a higher measure, we can use the Weingarten calculus, and it is possible to show that the average with respect to the ensemble of random matrix product states coincides with the average with respect with the whole Haar group, or the whole unitary group with the Haar measure. This means that the random matrix product states are a one design. And it's also possible to show that if we consider k equals 2, the random matrix product states ensemble is an approximate to design, and the epsilon part is proportional to the inverse of the bond dimension, meaning that if we make the bond dimension sufficiently big, and we are describing a state with more and more entanglement, and we are reaching the maximum expressibility. So this is in principle bad. Well, here I show you some data to prove that. So here you see that the random matrix product states are one design. Why? Because I'm plotting the trace distance between the average over the ensemble and the result of the average with the Haar, which, as I told you before, thanks to Weingarten calculus, we know that this is proportional to the operations with the symmetric group. In this case, k is equals 1, and we only have the identity, and this is what is called the maximally mixed state. So the trace distance between these two quantities is what is plotted here, and you can see that the Haar result, this is sampling, making a sampling according to Haar, is the black curve, and also that taking different bond dimensions, 2, 4, and 6, they are all in the same curve. This means that the random matrix product states are one designs. Here in the X, I have the number of iterations with where I compute the average. And you can also see that if we consider the homogeneous case, this is far from being a one design. And also, if we consider a bond dimension 1, it is not also. A bond dimension 1 is a circuit that has no entanglement. This is with respect to one design, and this is with respect to designs. Here I'm plotting the part of the fidelities that I told you before, and this is the average of the fidelities with respect to the ensemble of random matrix product states. And you see that there is a dependence with the bond dimension, which is okay. And moreover, you see that this expressibility, or this term, decreases with the bond dimension. And this is also very reasonable, because here I am considering a very small chain of 8 sides, And you see that for a bond dimension 8, which is the maximum that we can have for this size, we are reaching the higher value, which is this blue curve. So what we have here is that as we are moving the bond dimension to, as we are making it greater, we are reaching the approximate, the 2 design. So the random matrix product states are approximate 2 designs. So the result by Holmes must hold, and we have that the more bond dimension, this is the more expressive the ansatz is, the less trainable. So with this random matrix product states, we cannot bypass the result. We are in the same situation that before. If you consider entanglement, enough entanglement, you are in the 2 design case, and you have a lot of expressibility, and you cannot train it. So that's why I asked myself if there is another quantity that can help us to solve this. This is, can we find an ensemble of or can we find a circuit that only create states that have entanglement, but these states have a property that makes them easier to build than others with also high entanglement. And here enters the concept of complexity, because the complexity is the quantity that allows us to slice the Hilbert space when we are done with entanglement, when the entanglement is maximal. So I introduced to you the other topic. I don't know how what's the time, but so concerning quantum complexity, we have like 2 definitions that are complementary. One is the engineer point of view, which is the gate complexity. And the gate complexity tell us the smallest number of gates that we need for reproducing a given task with some tolerance. So we have and this is also a concept that arises in classical computation. But in the concept of quantum computations, it is what is the less number of gates that we need for computing, obtaining a state, given an original state. The other point of view is the geometrical one, which is like, if you want, a continuous version of the gate complexity. And the question is, or the quantum state complexity is what I have just said. How hard is preparing a state which is the target state, starting from a state which is the reference state? So this provides with a metric over the Hilbert space. And this, in the same sense, I would say that the fidelity provides a metric of the Hilbert space of the states that relates to the states. But this metric must be better than the fidelity. And what I mean by better, I mean that suppose that we consider a very complex quantum state, for instance, a state that describes a brain with all the neurons and all of that. And this state, this tensor product with a very with a spin which is in the 0. And we ask for the fidelity with other state, which is formed by the same state of the brain, but now the spin is 1. So in this case, of course, these states are orthogonal, so the fidelity is 0. But you can think, well, there must be very close, because the brain, which is very complex, is the same, and so these states should be the same. And this, in terms of complexity, is true. If you consider the complexity between the state with the brain 0 and brain 1, this is approximately 1. And why? Because it costs approximately the same to build this state from the fiducial state 0 or building this state from the fiducial state 0. So you see here the difference. And there is another notion related, which is the quantum unitary complexity, which is more or less forgetting about the states. And this provides with a metric in the unitary group. And of course, these two complexities, these two concepts are related. The complexity state, CR, CT, is the minimum unitary data of the complexity of unitaries. So this is the definition of quantum complexity. There is a very important conjecture by Brown and Susskind that say that the most local random circuits, that, like the one I have described before, have a complexity that grows linearly in t, in the depth or in time, for an exponentially long time. And this is important, it's an exponentially long time. So the entanglement of a quantum evolution has saturated much before, and now all the evolution that comes now changes the complexity, but not the entanglement because it is maximal. So we are exploring this vast majority of the Hilbert space, which enjoys the volume law. It is known also that the two designs, so remember that are the set of unitaries that enjoy the same properties than averaging over the R, if we restrict to k equals 2, are enough for capturing a scrambling. Scrambling is a property of late time dynamics of systems, of chaotic systems, that tell us that if you have some information at time 0, which is located in a small region of the system, when at a scrambling time, this information has spread over the whole system, and so the fact is that the two designs allows us to describe systems that are much more complex than ground states. That's a fact. And there are many states that are ground states and have high entanglement, and indeed may have the maximal entanglement for certain partitions or certain subregions. But they have low complexity, and this is, for instance, the rainbow state that that I work with during my PhD thesis, and this is the ground state of a Hamiltonian which is local and it's gapless, and it enjoys the volume law. Indeed, it violates maximally. You can see that if you consider this subsystem. It cuts the maximal number of bonds. So the entanglement entropy grows maximally. And but this is a ground state. So this should be this. If we write this in terms of matrix product states, they have a big bond dimension but a low complexity. So our ansatz should be able to capture this, should be able to find this ground state with high entanglement, but it has low complexity. So this poses the question, or the open question, of if we could avoid, of course, assuming that we have taken a local cost function, if we could avoid the existence of the barren plateaus by ensuring that our circuit is allowed to explore states with high entanglement, but restricts the complexity of the state. It does not create states that are more complex, that are not ground states. If we want to find a ground state, we don't need states that are describes a situation of a scrambling. So this is an open question. This is an idea that I have and I am working around. So I'm happy to discuss and to hear your opinion. So as a summary of this talk, of this introduction, I have give you a glimpse of what is a variational quantum algorithm. And I want to emphasize that it is a mixed algorithm that we use quantum computers for evaluate the complex part that a classical computer cannot do it efficiently. And we use the classical computer for the optimization. I have tried to explain what is the hard measure and what are the unitary K designs. The hard measure means the way of sampling uniformly the unitary group, and the unitary K designs are the way in that we can optimize this sampling according to our needs. I have introduced to you the barren plateaus that arises from the randomness of the circuits, and arriving to the conclusion by Holmes et al. That the more expressive the ansatz is, the less trainable. And then I have tried to bypass this condition, exploring first what happens if we play with entanglement with random matrix product states. And I have seen that since they are approximately two designs, they are too expressive, maybe. And we cannot bypass the problem using them. And finally, as a maybe solution to this, I have introduced the quantum complexity that using a sentence by Leonard Susskind shows that the entanglement is not enough for certain cases, and that we have to look other quantities. That's all. Thank you for your attention.
People have any questions? In the meantime, maybe I can start with one. If I understood correctly, approximate two designs are too much. They are too expressive, and that's too hard to train. But at the same time, a one design is not enough because it is not able to generate correlations, let's say. So then the ansatz that we are looking for should be something in between a one design and a two design. So it doesn't generate all the possible 2-point correlations, but it is able to generate some of them in order to be able to capture whatever ground state we are seeking.
Exactly, that's the idea. The idea, in my opinion, is that of course we try to express the things in terms of two designs or the hard measure because we know how to compute the things thanks to the Weingarten calculus. And the idea is that with two designs we are able to describe physical situations like the scrambling, which is something related that appears in quantum chaos. So the question is, do we really need so much expressibility? I mean, maybe our definition of expressibility, which is exactly the definition of an approximate K design, is not very useful to our purpose. Because of course I'm thinking also only in a variational quantum eigensolver. I'm thinking in a Hamiltonian that I want to solve. And I believe that the great majority of the Hamiltonians will have a ground state that may have high entanglement, it may be gapless, it might be topological order or whatever. It might be complicated, but well, complicated is not the word, because I want to say that it may have a big entanglement, high entanglement, but low complexity, because indeed the majority of the states in the Hilbert space they are unphysical, because they are so complex that we need like an exponential time to find them. And so they are in a quantum evolution, we don't consider them as physical. So my question, which is I'm not sure, is that maybe with these two designs we are considering states that are not interesting, but they preclude us to find ground states, and that will be a solution to the barren plateaus, a partial solutions, of course, but yes, that's completely the idea.
Okay.
Few questions.
I mean, I have more, so I could go on. Maybe this comes from the fact that I'm not too familiar with matrix product states, but because I think other people might not be either. When you mentioned homogeneous and inhomogeneous random MPS, the distinction wasn't too clear to me. Like, I mean, I understand where it stems from, but why did you make the distinction?
Yeah. So the idea is that so the matrix product state is obtained by multiplying these three tensor objects or matrices that are local. So for instance, so for instance, this I am considering as being 1/2. So we have the minus and the plus, or 0 and 1. And this box describes the site I, and the fact is that these matrices are the appropriate slicing of a bigger unitary, which is indeed 2 times the Bott dimension. And the Bott dimension is the dimension of this matrix A. So if this unitary is the same for all the states or for all the sites, then the A matrices are the same for all the sites. And then you have an homogeneous random matrix product state. And in that case, the color will be the same. I mean, it will be only orange and red, depending if you have the 0 or the 1, on each side. But if you consider the inhomogeneous one, then each side have a different unitary, and as a consequence, its A matrices are different.
Yeah, okay, but where does the inhomogeneity come from?
The inhomogeneity is just to reflect the fact that the unitary of the site M is different from the unitary of the site M+1.
Okay,
but and as a consequence,
this is related to the source of randomness.
Of course, because the unitaries are random, so the unitary here will be different with the unitary here. Yeah.
Okay.
But here in the homogeneous case, you are taking the a random unitary also, but only one unitary.
Okay.
Maybe in the chat or.
I think they are just wishing everyone a Merry Christmas.
Okay. Yeah. Merry Christmas. Come on, guys. One question.
Hi.
Hi.
I want to ask you about the hard measure, so you did parentheses, because I think you didn't come very clear to me, like you said that you choose like a certain ensemble of points, given ones in the unitary, like in the unitary group, and from there you can extrapolate like approximate the all the integers. But I think I didn't get that right.
Well, I cannot hear you properly. I will repeat the part of the har. Can you mute yourself, please?
Yes.
Thanks. Okay.
Who was speaking? Sorry, before you start, who was speaking?
Jaime from Hausen. I'm afraid I'm pronounced badly the surname. He was my student 2 years ago.
Okay.
So I think that he was asking about the hard measure, but I didn't hear properly. But so the idea of the hard measure is the idea, or not the idea, the hard measure is the quantity or the object that allows us to weight properly the elements of the unitary group. And since the unitary group of n qubits is something very difficult to imagine, I think that the best thing to do is to think in a sphere, in a 3D sphere. And then in a 3D sphere, you know that if you want to sample uniformly points or the reverse process, if you want to populate uniformly with points the surface of the sphere, you have to take into account that the shape of the sphere. You have to take into account that the equator is bigger than the area of the equator is bigger than the area on the poles. So in order to make an homogeneous population, you have to take that into account, because if you don't do that, so you will find that there are a bigger density of points in the poles than in the equators. And you have to, and that will not be a uniform distribution in the sphere. So that's what is behind the hard measure in the unitary group. And with the K designs, you do exactly the same, but up to a K order. So it's cheaper under a computational point of view.
Okay, Jaime, I hope that answers your question. If not, let us know in the chat, maybe. Sergio is asking a question in the chat. Nadia, I don't know if you prefer to read it yourself or you want
Hi,
to read
Nadir.
it.
Thank you for your talk. Can you recommend us some good optimizer to avoid barren plateaus in some way applied to VQA? I'm sorry. I don't know. I have not played with real optimizers. I have just stay in the comfort zone of the theoretical part. So yeah, I'm sorry. Maybe in Penny Lane, for instance, you can find some information, or yeah, Penny Lane has a very good explanation about the hard measure indeed, and maybe there you can find some information.
I can maybe add something to that. There was this papers from the group of Los Alamos where they basically showed that even if you have gradient-free optimizers, then you are also doomed for the barren plateaus. So
yeah, the barren plateau is not just don't just arise because of taking derivatives. It's something deeper. It's something. Of course, it seems that the crucial part is taking the cost function to be local. So the nature of the cost function is very important. But once you have taken that, there is some. I think that the structure of the Hilbert space is what really matters, and that's why playing with the complexity as a refined metric may be also interesting.
I have maybe a follow-up to what you were just saying. I had always thought about barren plateaus as the quantum analog of vanishing gradients in classical machine learning. But from what you just said, I think that's incorrect, or at least only partially true.
Because they are so also when you take no derivatives, right?
Okay. And also in the classical case with vanishing gradients, as I understand it, it's a progressive phenomenon in the sense that when you backpropagate and you go back layer by layer from the output to the input, the first gradients are okay because there are still not so many steps in the backpropagation. But then as you compound more and more derivative in the chain rule, then you start encountering vanishing gradients, and the level of vanishing increases as you go farther into the network from the output to the input. And so, as I understand it, you can have a situation in which gradients and thus trainability is okay in the end of the network, but the weights and biases at the beginning of the network remain unchanged during the training process. So you have sort of a random network at the beginning, and then you have a trained network at the end. I don't know if with the barren plateaus, the issue is similar in the sense that the end layers of the circuit get trained, but the beginning layers of the circuit remain as randomly initialized.
Well, I think that there is a similarity in the sense that it is progressive. So you play with the depth of the circuit. And what it is, what Cerezo and the group of Los Alamos saw in that paper is that if you consider a local cost function and shallow circuits, so small depth, there is a trainability. I mean, a depth that grows like the logarithm of the number of qubits. Then you can take a depth that grows like the logarithm of a polynomial of the number of qubits. And then you have like a transition phase to a depth that grows with the polynomial of the number of qubits. And then because of the other results, you know that it is there is no trainability. So yes, there is something that so the trainability changes smoothly, I would say. But I'm not sure if we can say more about because I'm not an expert in the classical case. But I will think about it.
Okay. I mentioned this because, I mean, I'm not an expert either, but from what I understand, the issue of vanishing gradients, it's a problem in classical machine learning, and I think that's why they use ReLU instead of sigmoid activation functions in deep neural networks. But I mean, it's an issue, but it's not a complete disaster in the sense that they find out that deep neural networks that work reasonably well, when they look at the weights and biases, they find that the initial layers remain random, the final layers are trained, and the model performs well. And I think the whole field of reservoir computing, where you have a random network at the beginning and then you have a shallow network that you train at the end, it was born from this discovery that in many cases the initial part of the network remained random. So.
That's interesting. Maybe there is a paper that have studied this, but I think that it's promising.
Okay. Well, if there are not more questions, let's thank Nadir again. Thank you for your talk. You introduced many complex concepts, but I think you did it in a very clear and systematic way. I really like the talk. So yeah, thanks. Thank you, everyone. Let me remind you again that we are open for submission. So feel free to propose a future seminar.
I just resend the link in case anyone did not catch it, so it's handy, and anyone who is willing to give a seminar, just you can copy the link and fill the Google Forms if you wish.
Okay. So then that's it.
Thank
Bye.
you.
Thank you.
Happy Christmas, Happy New Year.